Okay, this is a very brief discussion of Max Planck and the quantum. I'm not going to spend any time on Planck's life, although he had a very interesting and in many ways a tragic life. He survived 2 world wars, and each one of which took the life of one of his sons. But I want to concentrate particularly on his absolutely groundbreaking and world-shaking discovery of the quantum. And I'm going to show you slide by slide, just give you a very untechnical view of how he reached that decision. He was also called the reluctant revolutionary because it turned out that he didn't actually believe in what he had discovered for many years afterwards. And in fact, when he actually discovered when he made his understanding, that in fact it wasn't even clear that he believed in the existence of atoms at that point. Okay, the scientific background basically was that in Clausius and Thomson basically set the groundwork for what was called thermodynamics. In particular, the second law of thermodynamics and the discovery and discussion of entropy, which is absolutely vital for our understanding of the macroscopic behavior of bodies and any material in the world in terms of their pressure, volume, and temperature. And so thermodynamics was available to Max Planck. And the next important influence was Boltzmann. And Boltzmann now actually was the first person to really understand where the laws of thermodynamics came from in terms of the motion of molecules or atoms within a body. And he did a lot of work in doing that and set thermodynamics on a secure scientific basis. The next very important one, of course, was the great Scotsman, James Clerk Maxwell, who pulled together all the knowledge of electricity and magnetism up to 1860s or so and produced his 3 amazing equations. And I'm going to just tell you a little bit about that, as I am going to tell you about Boltzmann's work, because these 2 men had an enormous influence in the background that Planck used to make his discovery. So the scientific context of Maxwell was that he wrote down 4 equations which summarized everything that was known up to that point of electricity and magnetism. And he wrote them down in terms of 4 equations. And astonishingly, he managed to, if he joined a couple of the equations together, he could produce a wave equation. And that wave equation actually predicted an electromagnetic wave, which consists of oscillating electric and magnetic fields traveling through space at the speed of light. And this was a scientific background quite equivalent to Newton's laws of mechanics. And here is a little video which shows you what a wave looks like, electromagnetic wave traveling through space. And you can see the oscillating electric and magnetic fields, which turns out, thanks to Maxwell's equations, are at right angles to each other. And this is in fact what light and radio waves and electromagnetic waves of all sorts, from infrared to ultraviolet, through the visible spectrum, all the way out to radio waves and down to X-rays and gamma rays at the very high frequency or short wavelength end. Okay, now amazingly, what was extraordinary is that out of these 4 equations, Maxwell could calculate the speed of these waves in terms of 2 constants, which are universal constants. That is, they were part of the equations that had universal constants that had to be introduced to explain the electricity and magnetism. And astonishingly, he could predict out of this wave equation the speed of these electromagnetic waves. And of course, it turns out to be the speed of light. All electromagnetic waves traveling in vacuum travel at the speed, and it's extraordinary that could be predicted. And of course, it was verified by a whole variety of other people, both the existence of these waves and their speed and their properties. The next thing that came out of Maxwell's waves were he understood that an oscillating charge emits these electric waves. That is, if you take a charge and you wave it around in space, it will emit electromagnetic waves. And these waves will travel out into along into the universe through any medium that happens to be there, such as air or vacuum. And there they are again. Now, the problem that Maxwell was set, that Boltzmann was set to answer, was the color of material when it's heated. And you all know that when metal is heated, it starts glowing off orange, and then it gets red, and then it gets yellow, and then it gets quite white hot. And there's a little idea to give you how different temperatures go from dark red up through light red and yellow up to white hot. And why is this? Can we predict the electromagnetic frequency of the distribution of the electromagnetic waves that come off this heated body? Well, it turns out that in order to do that, Kirchhoff in 1859 had to find a black body as an object that re-emits all of the radiant energy incident upon it, that it is a perfect emitter and absorber of energy. The reason why this is important is that different materials hit in, depending on the context they're in, the place that they're in, the way in which they're heated, there tends to be some variation in that, and therefore you want to, in order to investigate the subject scientifically, you need to have something that is a standard, as it were. And Kirchhoff's black body, which absorbed all radiation incident on it and emitted all in very small amounts, of course, it was very useful in doing that. And here's an example of an incident ray, and it gets trapped inside the black body. And we all know about black objects in life. If you have a driveway that is black, you will find, of course, that snow doesn't sit on it so well because it tends to heat up more than the surrounding material, surrounding environment, and that's why it's called a black body. Now, the experimental results that Planck, and here he is here, had to explain was the intensity of radiation from a heated body. And here, if you plot wavelength on the x-axis and the bottom axis, and you plot the intensity of the radiation, you get here it indicated the visible part of the electromagnetic spectrum. This is the part that we see, all the way from blue at the short wavelength up to red at the longer wavelengths. But of course there's much else going on, and outside of that there's a whole distribution of radiation, and here's a graph of that at roughly about 7,000 degrees Kelvin. And the only thing that was known pretty much, or was a lot known at that time, but Wien's displacement law, that lambda t times the maximum was a constant. And that seemed to work very well. But every attempt to reproduce this distribution of radiation had failed miserably using standard classical mechanics, classical physics. And that was the problem that Planck was set to investigate. He had the following hypothesis. The walls of the black body contain little oscillators that can be modeled as little oscillating springs with charges at their ends. That is, he knew, thanks to Maxwell, that little oscillating charge would emit electromagnetic radiation. So he assumed that there were little oscillating charges in the walls of the black body, or of course in the walls of any material, but the black body was the one that he studied. And when you oscillate them, they produce electromagnetic waves. It's not clear at this point whether he actually believed in atoms, because that was something that was being investigated in a whole series of parallel investigations. But here's a little oscillating spring, and if you make it a really small one, and you make it look like that, that's what I'm going to indicate in my diagrams as an oscillating source of oscillating springs. And of course they can oscillate at different frequencies, and that's the key to the whole thing, is that you can now oscillate these two springs at different frequencies depending on what kind of, as we would say now, what kind of atoms they are, what kind of environment they're in, and so on. So the second hypothesis that he made is that the higher the energy of the spring, the higher the energy of the emitted radiation. That would seem to be self-evident almost. And the final one is that the frequency of oscillation equals the frequency of the emitted radiation, and the wavelength, of course, is dependent directly on the frequency, inversely. So here's Planck's radiation law, and he had a black body, and here are the oscillating little charges in the walls of this black body that are oscillating, and you notice that they're different frequencies. I've tried to indicate that, and they're oscillating at different frequencies. And if you do that and you do a calculation to try and find out what the electromagnetic radiation that comes out of this thesis, you'll find that it's a difficult thing to do, because one of the things that you don't know is how is the energy which is provided by heating the body, where does that come from, and how does it distribute itself across these atoms? Well, it turns out that Maxwell and Boltzmann, if you remember, Boltzmann's the one who invented statistical mechanics, Maxwell-Boltzmann distribution had answered this question for a gas. And Maxwell, in fact, had derived a formula for the speeds of molecules in a gas. This is the same sort of problem. If your gas is at a certain temperature, therefore it contains a certain amount of energy, how do the different molecules distribute this energy? Because they bounce into each other, they bounce into the walls. Maybe if they're in air, they've got a different variety of masses and so on and so forth. So you want to know what are the speeds of the molecules in a gas. They can go from ones that are quite slow to very high ones. So how do you decide that? Well, it turns out that he derived a formula for that. And this was, again, Boltzmann, who founded statistical mechanics. He gave a even more convincing derivation that related the formula to thermodynamic quantities. And this formula, that is the distribution of molecules in a gas, is called the Maxwell-Boltzmann distribution. But of course, it can apply to any small objects that have a variety of different energies, and the way in which each of the total energy of the body is shared by these little entities. And interestingly enough, there was a paper that I found called The Statistics of Crowd Fluids. It turns out that the movements of college students on campus and children on a playground fit the Maxwell-Boltzmann distribution. And the deviation was attributed to sexual inhomogeneity, meaning I think the little girls had a slightly different speed or a maximum energy than little boys. Anyway, this is what the distribution looks like. If you plot the speed of molecules against the number of the molecules, you get an oxygen, say at 300 K, about room temperature, you'll get a distribution like this. So the energy, if you notice, is spread from almost zero all the way up to a peak, and then it gradually tails off at the high end. That's the distribution of the speed of molecules, and this distribution was the one that Maxwell used, that Planck used, to explain how it was that these oscillating charges in the walls of his black body produced the energy distribution that he was attempting to explain. Here, I've just plotted about 250 meters per second at this temperature is about the speed of a molecule of the gas. Okay, back then to the black body, and here is Planck's radiation law. He's got the little oscillators, and as they oscillate, they each emit electromagnetic waves with energies dependent on the Maxwell-Boltzmann distribution. And what happens there is that the thing heats up, and there is a distribution, and the thing turns, in this case, orange, but it can turn at higher temperatures, it would be yellow or white. And if you plot the Maxwell Boltzmann, then the maximum entropy, that entropy is a measure of the disorder, so the thermal equilibrium when the disorder is maximum, and that's gives you the average temperature and the distribution indeed of temperature across the body. So here's Planck's radiation law again. Remember the intensity of radiation, we plot wavelength against intensity. There's our the little part that we see, the part of the electromagnetic spectrum that is visually available to us, and there's our distribution. And there had been many attempts to fit this distribution. The particular one was the classical distribution, which did a terrible job at fitting it, and this was the reason that Planck had to make, it turns out, an absolutely extraordinary decision. And Planck's formula was absolutely perfect. He found the formula that fitted beautifully. This took a long time, and it was very experimentally difficult to get a decent black body that did it, and so on and so forth, but this is what turned out. So how did he do it? Well, there's his formula, by the way, which is a little complicated, but that fits this experimental distribution perfectly. And the reason is that he managed to do it, and this was 1900 that he presented his results in one of the big scientific meetings in Vienna, was using the experimental measurements, Kirchhoff's black body, Maxwell's equations for electromagnetic waves, and the Maxwell-Boltzmann energy distribution. He could produce a perfect fit to the experimental radiation law. And he exactly reproduced the experimental results, but he had to make the most extraordinary suggestion that the oscillators emitted their energy in tiny lumps, which were proportional to the frequency of the oscillations, that they didn't emit them smoothly. There were certain energies which you simply couldn't get out of a given oscillator. They came out in little lumps, either 1 times, 2 times, 3 times a fundamental quantity. And the fundamental quantity was called a quanta, and the energy of each one was called, the energy was proportional to the frequency multiplied by Planck's constant, as it was later called. And these energies then had to be fixed in one place. Einstein came along several later, and he finally solved it with the photoelectric effect. Electrons, in fact, in a metal can be treated as if they were free. There's a sea of electrons. Here's my example of electrons flowing through a metal rod, and you can see they oscillate up and down. And if you shine a light on them, photons coming in, it turns out they knock out electrons from the metal, and by calculating the energy of the electrons coming out and compare them to the frequency, or that is the energy of the photons going in, you can show that the photons have to have an energy which is equal to Planck's constant multiplied by their frequency. And that was exactly what, and so Einstein, in fact, made the extraordinary leap then from Planck's quantum, a very sort of abstruse and more difficult calculation. He showed that photons behaved in this funny quantum way as well, and that pretty much set the same people then began to really believe what was going on. And even Planck, who had thought that his calculations were purely a mathematical game that managed to fit the distribution, he began to then believe in the existence of what were called the quantum